Hello everyone, and welcome to the National Stock Assessment Science Seminar. My name is Bailey. I coordinate this monthly seminar series that highlights interesting advances and topics in stock assessment science. Before we get started, I just want to make a quick announcement. I'm currently organizing next year's seminar schedule. So if you are interested in presenting your work, please check the Google appointment scheduler to view available dates and reserve a slot. I'll post the link in the chat. And yeah, feel free to reach out if you have any questions. And a big thank you to those who have already booked a slot and are willing to share your work with the community. And today I'm very excited to welcome Jane Sullivan. Jane is a stock assessment scientist at the Alaska Fishery Science Center. Her work focuses on informing fishery management through applied data analysis and experimental gear research. Her work includes developing software to improve existing data processing and stock assessment frameworks, as well as advancing methods in fisheries population modeling. In today's seminar, she will discuss causal models as a scientific framework for next generation ecosystem and climate linked stock assessments. Without further ado, I'll hand it over to Jen. Thank you all for joining us.
Thank you, Bai. Let me get shared here. Okay, so thanks so much to everybody for tuning in. I'm really excited to be here representing a much larger team from the Alaska Fisheries Science Center and beyond. So a special thanks to Juliet and Cole, who contributed a lot of content to this presentation. I want to make sure they get full credit for the good parts. Okay, so why this talk? As assessment scientists, our job is to provide scientific advice to manage fish stocks. The productivity of these stocks, their ability to reproduce, survive, and grow varies with the environment. This figure shows projected increases in sea surface temperatures and net primary productivity between the past through the end of the century. These changes are not expected to be uniform. They will vary by region and are expected to affect the base of the food webs in ways that cascade up to fish populations. So in order to provide the best scientific advice, we should continue to develop tools to understand and predict changes to the stock as the environment changes. We can, of course, use environmental and ecosystem covariate data to help improve our understanding of stock productivity, but the reality is we rarely do. As of 2023, only 8 out of 232 US stock assessments included an environmental covariate in a quantitative way, so just over 3%. This analysis highlighted a major gap. Most of our assessment models rely on random deviations to describe variability in stock productivity, and very few explicitly model how the environment influences recruitment or other key processes. So why is that? We think part of the reason is that we often rely on correlations. We follow a data-driven approach that focuses on patterns and not underlying causes. And if we want to understand mechanisms and improve our predictions and understanding of productivity changes, we need tools that go beyond correlation. And that's where causal models come in. Here's just an outline of the talk for today. First, I'll describe the status quo. We'll talk about how we currently handle annual variation in stock assessments and why those approaches have limitations, especially when we try to include environmental drivers. Second, I'll make a case for causal models. I'll talk about both new and more familiar concepts and how all of these acronyms you've heard floating around, DSEM, DAGs, ESPs, and maybe even SCEAM, they're all just tools. And when we combine these tools, they can help us move forward in a more structured way to understand changes in stock productivity. Third, we'll go through a case study with Gulf of Alaska pollock. That example will show how causal modeling works in practice using real stock assessment data. Then we'll discuss potential on-ramps to management. and how we can connect this work to existing frameworks like our risk tables and ESPs. And finally, we'll wrap up with a few thoughts on what's next for our team, and then maybe some recommendations for this broader line of work. Okay, so what are the main approaches currently used to model time-varying processes like recruitment and stock assessments? So the most common is the empirical or stochastic approach. Here we acknowledge that there is annual variation, often due to unknown or unmeasured drivers, but we do not model those drivers explicitly. Instead, we treat the variability as a random process. For example, recruitment deviations might be assumed to be independent and identically distributed, or follow a first-order autoregressive process. Second, we have the mechanistic or regression approach. And this can be implemented in a couple different ways, or a few different ways, really. There's the standard method where the covariate is regressed directly on a population process like recruitment or catchability. This method is widely used in stock synthesis, and it definitely adds a layer of biological realism, but it has challenges, especially when covariates are noisy or correlated. Alternatively, the mechanistic approach or regression approach can be implemented using state space methods. And for the last 6-7 years, this has been really the state-of-the-art method. This is how environmental covariates are incorporated into the Woods Hole assessment model. This method treats observed covariates not as exact values, but as noisy measurements of a true unobserved environmental state. And that allows us to propagate environmental uncertainty throughout the assessment and may improve inference and projections. So just kind of taking a look at these different methods, each approach reflects a different philosophy, from the we know there's variation, but we don't know the cause, to we think we know the cause, to we think we know the cause, and we want to account for uncertainty in both the data and the process. But there are limitations to the regression approach. A central goal of ecology is to understand what causes variation in ecosystem function. But this is difficult because our systems are extremely complex. The variables we think might matter, like temperature, chlorophyll, or zooplankton, are often correlated with each other or driven by shared factors like climate indices. And that creates two main problems for regression models. First, regressions assume that covariates are independent. But like we just discussed, in ecosystems, they're generally not independent. And if we skip over that correlation structure or how those variables are related to each other and to the process we're trying to understand, and we just throw a suite of variables into a multiple regression, we risk getting biased coefficient estimates or even the wrong sign on the estimated regression coefficient. And that happens because of unmeasured confounding. That's what I'm trying to show here in this toy example on the bottom. So, imagine we fit a regression model where fish recruitment is a function of sea surface temperature and zooplankton. But if we look at the true data generating process, it includes a climate index, here the North Pacific Index, that is a driver for both sea surface temperature and zooplankton. That missing variable or confounder biases our estimate of the different effects, and it could easily lead us to the wrong conclusions. So the second issue with regression is the fact that because our suite of environmental variables are often correlated, this often leads us to choose just one covariate, for example, our favorite, temperature, to represent all environmental or ecosystem variability. And that choice makes it hard to communicate mechanisms or explain changes over time. So I want to emphasize regression can be extremely useful for prediction, but it has major limitations when we're trying to understand the underlying mechanisms. So causal modeling. Causal modeling builds on regression by asking deeper questions. So not just how well a variable predicts an outcome, but whether it causes it. This framework, which is laid out by Pearl and others, works not only with experimental data, but also with observational data, which of course is what we typically rely on in fishery science. And to visualize causal assumptions, we use something called DAGs, or directed acyclic graphs. These might sound unfamiliar to many, but the idea is something that most of us already use. If you've ever thought something like recruitment was low because sea surface temperatures were warm and zooplankton were scarce, then you've already formed a mental DAG. And DAGs make this kind of thinking explicit. It's a formal way to represent hypotheses about causes and effects. And as Grace and Irvine describe it, a DAG is a translation of the scientific ideas into a set of testable expectations. Each of these arrows represents the movement of information from the past to the present. And so just kind of thinking about our toy example, this is in fact a DAG where sea surface temperature affects zooplankton, which affects recruitment. And then we have that climate index, the North Pacific index, that influences both sea surface temperature and zooplankton. And again, I want to emphasize that this structure helps us clarify our assumptions and gives us a map for how to test them. So just looking at kind of what this might look like in practice, here we've laid out a step-by-step framework from Grace and Irvine for using causal analysis in ecological modeling. It starts with background knowledge. And so for us, we gather what we already know about the system from our ecosystem status reports, our environmental and socioeconomic profiles, published process research, and our subject matter experts. Then we draw a causal diagram, or our DAG, that represents our hypothesis about how the system works. And this is where we define the relationships, consider possible confounding variables, and clarify our assumptions. Next, we test those hypotheses using structural equation modeling or extensions of it. And we'll cover the statistical part of this in a minute. But this third step, the modeling, allows us to estimate the strength of each link, test for missing links, and examine both direct and indirect effects. Then comes the interpretation. We're not just plugging in variables and getting coefficients. We are, in fact, evaluating assumptions and refining our understanding. And it's this evaluation and refinement of assumptions is what allows us the room for iteration in this framework. These models become part of the learning process, and we might expand or adapt them as new data or insights come in. So how does all this come together in practice? Let's walk through a case study that my friends in Alaska will be familiar with, the Gulf of Alaska pollock assessment. This work was led by Juliette Champagnat, who is a former postdoc of ours at the University of Washington Alaska Fisheries Science Center, and Cole Monahan, who's the assessment lead for Gulf pollock. Pollock is a great test case for causal modeling, which is part of why it was chosen. We have a long and well-documented history of recruitment variability, a really strong foundation of process research. It is a data-rich assessment with an age-structured stock assessment model that's coded in Template Model Builder. And again, one of the defining features of the stock is the large variation in age 1 recruitment, including some very strong year classes that dominate total biomass. And that makes recruitment not just interesting, but a process that is critical for both science and fishery management. And then importantly, we had a wealth of covariate data available through the Environmental and Socioeconomic Profile, or ESP. A number of ESP covariates had already been explored qualitatively or in exploratory analysis, but many had not been included formally in the assessment framework. So here I'm showing the available ESP time series. Each of these panels is one potential covariate that we looked at. These ESP indicators include physical variables like sea surface temperature or wind direction, biological variables like euphosit or copepod biomass, and then predator and competitor indicators as well. But as we saw earlier, we can't just throw all of these covariates into a multiple regression and hope for the best. And instead, we worked with subject matter experts to identify plausible causal pathways and construct a diagram that reflects how these variables might be connected and ultimately if and how they affect recruitment. So here's kind of the initial draft where this is a conceptual model that was developed, and in it we show the hypothesized relationships between these various ESP indicators and pollock recruitment. This model was built collaboratively using the ESP as a foundation and then incorporating expert input from biologists and ecosystem researchers. The goal was to lay out a comprehensive view of all the pathways that might influence recruitment. The hypothesized positive associations are shown in blue, and the negative associations are shown in red. And this is like essentially a DAG, just drawn in a more familiar ecological format. And so each of those arrows represents a potential causal pathway. And again, just emphasizing that this isn't just a correlation, but a directional relationship based on our process understanding. Some of these pathways are direct linkages to recruitment, like the link from the young of the year abundance to recruitment, and others are indirect, moving through multiple stages. So, for example, sea surface temperature points to, among other things, copepods, then young of the year condition, and then recruitment. So this step of assembling the background knowledge and developing this initial conceptual model is really key to making causal modeling operational in stock assessments. But to move from concepts to a model that we can actually fit, we needed to simplify and select a smaller set of pathways that were biologically plausible, supported by the data, and representative of our best guesses at how the system really works. So that underlying data generating process. So in other words, we needed a set of candidate DAGs, and one of those is what you're seeing here. This diagram, again, is capturing a reduced set of causal pathways that were drawn from the broader map. And importantly, this structure represents testable scientific hypotheses. It tells us what we think causes recruitment to be high or low, and which variables we needed to include to isolate those effects. So big step here. And after we've worked with our experts to define our hypothesized causal relationships, the next step is to estimate how strong those links are and how certain we are about them. This is where DSEM, or dynamic structural equation modeling, comes in. DSEM is the tool we use to estimate lagged and simultaneous causal effects. So for example, using DSEM, we can test whether temperature from last year influences recruitment in this year while accounting for other variables in the system at the same time. DSEM lets us estimate the strength and direction of each causal link, and it handles missing data and time series smoothing using an autoregressive structure. So this figure on the right is the output version of the DAG. So same causal structure, but now we've added estimated effect sizes on the arrows, where the red is the negative relationships, blue is positive. The numbers show the strength of each effect, and the stars indicate statistical significance. And basically the movement from the past figure to this one is that we're no longer saying we think these links exist. Here is where we're actually testing them, quantifying them, and understanding their relative influence on one another in recruitment. So just a quick overview about how DSEM works under the hood. I think about DSEM as a statistical multi-tool. It combines elements from a lot of different modeling frameworks, so time series models, structural equation models, dynamic factor analysis, and it pulls them together in a single framework. I'll be the first to say I'm not the expert on the DSEM math, except that I can just confidently tell you that the math is hard. This is Jim Thorson's world. He's the DSEM R library package developer, which was built in TMB. And DSEM is just really what makes this whole thing possible. And so while I'm not going into technical specifics, the key takeaway here is that this tool gives us the flexibility to go from a conceptual DAG to a working statistical model that efficiently handles real-world data problems. So this is where we can go from hypotheses to actual estimates and interpretation. And how does this connect back to stock assessment? So this is the nuts and bolts. What we've done is embed DSEM directly into a state-space stock assessment model using Template Model Builder. And we call this framework the Structural Causal Enhanced Assessment Model, or SCEAM. So we're the SCEAM team. On the left, we have all the typical components of an assessment, the catch data, survey indices, age counts, et cetera. And these inform population parameters like fishing mortality. In the middle, we have our population process of interest that's treated as a random effect. So for example, recruitment deviations. And what SCEAM does is connect that process of interest, like recruitment, to the right-hand side, which is where our environmental covariates and our causal hypotheses are articulated in that DAG. So rather than just assuming recruitment varies randomly, we can say, all right, let's use the DAG, fit it with DSEM, and see if environmental indicators can explain some of that recruitment variation, all while still operating within the full stock assessment framework. Let's take a closer look at how SCEAM works and what makes it really powerful and exciting. SCEAM gives us a flexible general framework that can replicate or extend the functionality of many existing stock assessment models, including how stock synthesis or WAM incorporates environmental covariates. Here in this diagram, you can see how the different models and assumptions fall along a spectrum. On the left, we have models with simple assumptions like IID recruitment. And then as we move right, the models increase in complexity and structure, from an autoregressive to regression to dynamic factor analysis or DFA, and finally to a full causal model. And in a DFA, just side note, multiple environmental time series are reduced to one or more latent or unobserved states that are estimated and in turn directly affect the population process of interest, like recruitment. SCEAM can do all of these using the same code base and an easy to learn interface for specifying interactions. This means we can build a model that's as simple or as complex as we need, depending on our data and scientific understanding. So this isn't just about adding complexity. I think it's really about being transparent with assumptions. And so with SCEAM, every arrow in the DAG corresponds to a causal link in the model. And this framework forces us to make our assumptions visible, testable, and more intuitive to communicate with colleagues and with fishery managers. So how did it actually perform? Here are the results from applying SCEAM to pollock recruitment. So we tested a range of models, including simpler ones like IID, AR1, and regression. We tested a DFA and 3 causal models of increasing complexity. The estimated effects, shown again as those red and blue circles, were not only consistent among the DAGs, but also with our hypotheses based on domain knowledge. So the hypotheses that we formed when we were creating that initial conceptual model. And that was true for all except one environmental link, or one of the linkages. That was Young of the Year condition, which was estimated to have a negative relationship in our models, negative relationship with recruitment. And that was the opposite of our expectation. And this finding actually pushed our team to go and communicate more with our ecosystem experts about, how we can improve the underlying data or update our hypotheses or pursue process research to better inform this linkage. The best fitting model was the DAG representing moderate complexity. So this is outlined in red here. This model reduced unexplained recruitment variance by 69%. So basically cutting that recruitment standard deviation from 1 to 0.54. So really, really dramatic reduction in sigma R. It also improved 1 year ahead recruitment projections. And so based off of these results, this model isn't just fitting the data better in the past, it's also improving future predictions. And it has fast and stable optimization. This optimized in under 2 minutes. So before I move on to the next part of the talk, I hope you're getting excited. This is not simulated data. This wasn't just an academic exercise. This is a real stock assessment that supports the management of a $40 million fishery. And this the SCEAM framework was able to improve it by adding structure and process understanding through causal modeling. We see causal analysis not just as a modeling tool, but as a scientific framework for the next generation of climate and ecosystem linked stock assessments. This figure shows what we might call an idealized workflow. It's iterative and starts with background knowledge and finally ends with improved understanding, hopefully better science and ultimately management. You'll see in the cycle, it includes not just the statistical modeling, but also collaboration, monitoring, and refinement of our processes. It's a framework for doing science, and we think it's better aligned with the way ecosystems actually work. And how did this play out in practice? So that was the idealized framework, but what did it look like in reality? So first, we found that the data that we already have from the ESP explained a substantial amount of recruitment variability and improved short-term predictions. But the biggest takeaway wasn't just the results, it was the overall process. Building and testing causal diagrams was a valuable way to pool expertise and generate new insights. And it's just a good reminder that modelers are not the only ones at the table. Co-developing these causal maps gave ecosystem scientists and assessment scientists a shared structure for collaboration and highlighted the importance of process understanding throughout the assessment cycle. There's a lot of room for improvement and avenues for growth. So in my mind, for pollock, a lot of this was a natural extension of the ESP process, going from focusing on identifying and developing indicators to actually modeling those causal mechanisms. Another area for growth is strengthening our toolkit for establishing causality, especially with the observational data that we rely on. Meeting this kind of causal standard is hard. And so while I won't go into detail here on the methods, the point is that we need practical methods to evaluate whether a covariate helps us identify a causal effect or whether it introduces bias. And finally, this work is pushing us to think harder about how causal analysis can inform fisheries management. And so that's where we're headed next in this presentation. So as we think about on-ramps to management, this quote from the Stock and Miller WAM paper, I think gets at something really important. It reminds us that the primary goal of stock assessments is to provide actionable management advice, not just to explain every ecological relationship, no matter how interesting or biologically plausible. This is an important check on our ambitions, because even if an environmental covariate does affect productivity, that doesn't automatically mean it will improve our management decisions or advice. If the effect is small, uncertain, or inconsistent, it might just add noise and confusion. And in some cases, as this paper noted, it could even lead to worse outcomes. So there's a critical however here. If we can identify strong mechanistic links, then incorporating environmental covariates may help reduce uncertainty, which is certainly what we showed with the GOA pollock case. So this slide lays out 4 potential pathways that SCEAM could connect to and strengthen our existing management frameworks. First, strengthening the ESP process. Our ESPs already give us valuable information, but they often stop short of making testable hypotheses about causality in our systems. SCEAM helps us take that next step by organizing covariates into causal diagrams, prioritizing the right indicators, and clearly documenting our assumptions. Second, we think SCEAM can support risk tables or other summary tools we use to help document decision-making behind potential ABC reductions. Right now, our risk tables rely on expert judgment, and they're qualitative. SCEAM provides a way to back up those judgments with model-based outputs, like the predicted effect of warmer sea surface temperatures on next year's growth, for example. We could even use or imagine a scenario where those predictions are used to develop triggers or buffers into harvest control rules, especially if the causal effect is strong and actionable. I think that this would allow for more predictable management outcomes if, for example, exceeding some marine heat wave threshold triggered a specific percent reduction in ABC. That would be a more predictable management outcome, for example, that could come out of SCEAM. Third is in scenario planning and management strategy evaluation. SCEAM gives us a framework for simulating the what if or counterfactual scenarios like warming, prey collapse, or predator shifts, and evaluating their impacts on productivity and stock status. Well, at least productivity for now. These kinds of projections help us plan for change, not just respond to it. And finally, we've been thinking a lot about bridging the gap between research and operational assessments. We saw it in GOA pollock, where causal modeling reduced uncertainty and improved short-term forecasts. But the challenge now is to translate those improvements into our management reference points and other parts of the assessment and management system. So this is how far we've gotten, but I think there's a long way to go here, and I'm interested to hear from the group what other on-ramps to management you all see for SCEAM. And of course, we can't apply this kind of modeling everywhere, and so here are a few things to consider when prioritizing stocks. Is there an ESP or recommendation to create one? This information will tell us if there's already a foundation of knowledge, data, and stakeholder engagement. And if an ESP exists, SCEAM can help formalize and test those ecosystem linkages. Second, is the stock fully utilized or high value? When a stock is economically important, there's a larger incentive to reduce uncertainty and improve projections. But of course, the flip side is that there's also going to be larger consequences for a high value stock if we get the causal model wrong. Third, I think we should be thinking about the current condition of the stock. For stocks that are declining or rebuilding, SCEAM can help us determine if ecosystem drivers are playing a role. And finally, thinking about that scenario planning, how vulnerable is this stock to future change? If a species is sensitive to things like temperature, prey, or habitat, that stock might be a good candidate for scheme-based scenario planning. And then on the right, I've just documented some headquarters tools that can help with this type of prioritization, including the gap analysis and the climate vulnerability assessment tools. So similar to the last slide, we're at the beginning of this conversation, and I'm interested to hear what else others might be considering if looking to apply SCEAM. So heading towards the end of this presentation, this slide is a reminder of the stakes. When we make causal claims, we're saying that this variable doesn't just correlate with an outcome, it helps cause it, and that's a powerful statement. But if the map is wrong, if the linkages are misspecified, or if real-world relationships shift, our models can fail. And in fisheries, where we work with messy observational data, our expert knowledge blends both mechanistic understanding with insights from correlational studies. And if our assumptions or methods are flawed, that risk carries through to our projections and ultimately, potentially, our management advice. So what do we do about that? One answer, I think, is transparency, and those DAGs really shine in this respect. They're not just modeling tools, they make our assumptions visible, and they give scientists and stakeholders a shared language to ask questions like, what are we assuming drives recruitment? What are our biggest uncertainties? And what data would help us test this more rigorously? So as we think about implementing SCEAM more broadly, just a few thoughts. First, we need to be rigorous about defining the structure of our maps. That means being clear about the assumptions we're making and the uncertainty that comes with them. Second, we need to be transparent and critical about the data and studies we rely on. Like I said previously, much of our process understanding comes from observational data. Third, this entire process highlights the importance of process research and continued monitoring. We need robust studies and sampling programs that help us identify mechanisms that drive population processes like recruitment. And to the extent possible, we should be supporting lab studies because they are our gold standard. And finally, we have to keep our stakeholders in mind. If we want to maintain trust and credibility, we need to communicate our assumptions clearly and avoid overpromising. So this slide is a reminder that this work is really exciting and promising, and we should proceed with caution and humility. So this is my last slide. I just want to kind of share where we're headed next. So first, super exciting. We're working to integrate SCEAM into AFSC's multi-species model, our Seattle, led by Grant Adams. This integration of SCEAM into an existing framework opens the door to test other population processes like growth or natural mortality through that causal lens. And we're kind of along these lines, because it's a multi-species model, we're also exploring how multi-species DAGs could be specified. For example, exploring associations among recruitment for multiple stocks, or linking recruitment in one species to mortality in another, is another example. We're expanding simulation testing to understand what happens when you get the DAG structure wrong, because that is a very real risk, and it's important to understand the consequences. And finally, we're also increasing our capacity at the AFSC through a couple new case studies and regular meetups to discuss papers and code. One of the case studies here, Gulf of Alaska air-tooth flounder. This is a lightly exploited stock with a treasure trove of process research. So this makes it a great candidate for testing causal hypotheses, but also potentially a good case for exploring how SCEAM might be implemented as an operational assessment. The other is Atka mackerel in the Aleutian Islands. This is a fully exploited stock with a clear recruitment bottleneck. And I've been working with a team of subject matter experts the last few months developing a new ESP for Atka, and SCEAM is really the focal point. And so this is kind of bringing in a new way to develop ESPs. And finally, Jim Thorson continues to develop the DSEM software itself, improving usability, extending model functionality, and supporting broader adoption. So that is the end of my talk. Thank you so much. And again, lots of credit to everyone involved with the SCEAM team. We miss you, Juliet. We hope you're thriving in your new job. I've included some resources for you all to follow up on, including very exciting, a preprint of Juliet's manuscript, along with a few recorded talks from Jim and Juliet, and a link to the DSEM art package vignettes. I look forward to your questions.
Awesome. Thank you so much for your presentation. Audience, this is Cassandra again, and we have plenty of time to answer your questions, and we would love to hear them. And the questions are rolling in, so we'll get right to it. For our first question, very interesting talk. What are the advantages of using a causal model compared to machine learning-based models? Alternatively, is there a way for machine learning models to assist in uncovering or improving causal relationships?
It's a great question, and I'm not sure I'm the absolute best person to answer it, but I think that the biggest advantage of using a causal model really is about that transparency. A lot of times my understanding is that the machine learning based models are more of a black box. And so being really upfront and transparent about our assumptions going into this, I think can not only help us improve the science, but also help us maintain credibility. That said, I think that other people in the team, might express a different viewpoint, and certainly they'll follow up with you if they have that.
Great. Thank you for your response. Our next question. How does this work for a species and region without the same level of data collection at many different life stages?
Yeah, I love this question because I don't necessarily work with super data rich stocks, and right out of the gate, I'm like, okay, cool, this works for pollock, one of our most data rich stocks. But how is this going to work for our data moderate or even our data poor stocks? And this is where, kind of thinking back to that spectrum of models that DSEM can fit, and the different assumptions embedded in those models, I can just say that I've seen this work successfully for a data moderate case, where we have limited observations at the larval stage, at the age 0 stage, even up to age 1. But it's really kind of getting back to that, understanding of maybe some of those physical drivers, or thinking about other ecosystem data that we might have. And yeah, I think it's important to kind of remember that the causal models can collapse down into, simpler versions like that DFA, or simple regression, or using the stochastic approach.
Thank you. Our next question, DSEM is a pretty good multi-tool, but how do nonlinear dynamics fit in? Example, thresholds, parabolic relationships, etc., that could be fit with a GAM?
Yeah, so I think that that's coming. I think that accounting for nonlinearity and those threshold dynamics is very important, and something that hopefully Jim will build into DSM very, very soon. Because you're right. Right now there is that assumption of linearity.
Great, thank you. Our next question, do the estimated environmental relationships depend on whether the estimation is made inside or outside the assessment model?
Great. So the question here is, and please folks like head over to the DSEM tutorials to learn more on this and also listen to some of Jim's past talks. But DSEM wasn't necessarily developed to be embedded into a stock assessment model. It can very much be used as an external model, for example, fitting the output of a stock assessment model like recruitment as the outcome. And the answer is they match up very, very well.
Great, thank you. Our next question. The use of DAGs seem great for the reasons you mentioned, but what about feedback loops? Would traditional mechanical models, BCG ecosystem, still play a role at assessing feedbacks?
Yeah, and I am not I'm not well equipped to kind of respond directly to that question, except to say that the time series component of it is really extending that SCEAM. So I'm still learning about kind of that feedback part of this, and yeah, I should have said right out of the gate that like we are learning right now, and so yeah, it's a great question, and I'm excited to be here to kind of hear those questions and think about the questions we haven't answered or haven't asked or answered. So thanks.
Thank you. Our next question, from a DAG, you can elicit a series of conditional probabilities that hold given the DAG. You can use those to get an idea of how consistent DAG is with the data. A tool like Daggity can generate those statements. Oh, I guess it wasn't a question. I'm sorry. I didn't read the whole thing.
Look at you, Roy. I agree with you. And those are true things. And so I mentioned it very briefly. I didn't want to get into specifics, but yeah, thinking about data consistency, backdoor criterion, basically making sure that we're identifying covariates correctly and estimating those linkages without bias is a critical step to this. And Jim and others are working on developing practical tools that are more tailored to some of the extensions in DSEM to make those tools more accessible within the package. But yes, in the meantime, so Daggy is a great tool, and it's been really fun learning to use it.
Awesome. Thank you for your response. Our next question, you mentioned co-producing the causal linkages and mental models of the system as part of the process. Are you engaging with fishers and industry in that process or other groups?
I'm not yet, but I wasn't able to attend the pollock workshop in January. I think some fishery stakeholders may have attended. That's kind of where they worked on refining that initial conceptual model. But I think that there's a lot of potential to include stakeholders in this process. Like I tried to emphasize, these DAGs, they create a great tool they're a great tool for communication. Gives us that common language. And yeah, I think, I don't think we've talked a lot about kind of environmental and ecosystem variables, but we also have, in some cases, some rich socioeconomic data sets. And of course, we have processes in our assessments that are potentially influenced by those. And so I think, both getting information about the ecosystem and the broader social system is really important. And yeah, I just don't think we've fully been able to communicate with our social sciences colleagues well enough to be able to make sure we're doing that in the right way. Something we've discussed, though.
Awesome. Thank you so much for your response. Our next question, what was the pollock YOI condition index that gave negative relationship with recruitment?
Yeah, I believe that was from one of the nearshore surveys. Yeah, it's from the EcoFoci summer survey.
Awesome.
Thanks, Yasik.
Thank you. And then that was all the questions we have in the queue. I'll give it a few more seconds just in case someone was in the midst of typing one. We do have a few more minutes left. I'd hate to cut someone off. But if not, then we will go ahead and wrap up today's seminar presentation. Okay, and nothing has come in, so I think we are good to go. Thank you again, Jane, for joining us today and sharing your work with us. This was really great. And thank you, Bai, for organizing today's event. Audience, please join us again at our next National Stock Assessment Science Seminar. Take care.